Hi, welcome to the first computer musing of the. There's an echo. Is it okay? Okay. Welcome to the first computer musing this quarter. I expect to have another one on 13th of December. I'm sorry I can't do it during finals week, so this is the Monday after finals week, and so I know a lot of you'll be gone home. If so, you can watch it on TV. The Stanford SCPD, whatever it stands for, has been very good about putting the back lectures in this series online, and I've watched most of them again, and I realized that I had better stop telling the same jokes all the time, and I have to pay more attention to other little mannerisms that I'll try to get rid of. But anyway, it is possible. Let's hope to watch this again later on, in case you want to see, why I made certain mistakes or whatever it is. And also, we hope this will be a resource for future people who are interested in the cool stuff that I might have. The point of these lectures is whenever I hear something that I think is pretty interesting that I don't think is in any of our other curriculum, I can't resist coming in front of noise and telling somebody about it. And today is a special case. My title today is "Hooray for Probability Theory," and really that's a sentiment I felt very strongly twice this year when I had been working hard on a problem for a long time. Well, for me, a long time is 2 weeks. But anyway, I've been working very hard on these problems, and I decided to give up on it. And then all of a sudden, wake up in the morning and say, wait, probability theory might help. And then I find not only a way to solve the problem, but a way that's easy and beautiful and so on. I hope you agree when you see the two things I'm going to talk about. In fact, the first one I'm going to talk about is something I learned about just at the end of June, and it's so simple, so useful, so beautiful that I think it should be in all books on mathematics. But I had never heard about it until last June, and I thought, by the time you get to be as old as me, it's not very often that you hear something that has all those characteristics anymore, because most of the simple stuff presumably has been well hashed over. And maybe a lot of you will know this. It's just that it was just me that didn't know it. But anyway, if I had known about it before I retired, I certainly would have put it in my book Concrete Mathematics. And now I was able to sneak it in as exercise number 62 in Art of Computer Programming. But I'm glad to see so many people here today, so that you can pass the word on, because it's really a beautiful result. Now, how can anything possibly live up to so much hype? Well, we'll have to see. So I guess I better just write down a theorem and see, and then we'll add to the theorem. But the first result comes out about probability theory, and so let's. Well, I won't write down a theorem. That's a boring way to. Let's suppose that I have n coins, and I'm going to flip each coin, and I want to see what it's the odds that or the probability that I get heads k times. So I've got coins, and the coins are each are biased in a certain way. So let's say that P1 or P sub j is the probability that coin j comes up heads, and then qj is the opposite, that it doesn't come up heads, it comes up tails. And for the sake of to be definite, I'm going to assume that the coin does not come up on its rim, so that Pj plus Qj equals 1. Now, has anybody heard this problem before? Probably. Okay. Furthermore, now we want to know, so we can form the generating function, the polynomial q1 plus p1z, q2 plus p2z, and so on, all the way up to qn plus pnz. And this will be some polynomial a0 plus a1z plus a nz to the n. And a sub k will be what? That'll be the probability that k times, or k heads were obtained during these causes. Okay, each toss is independent of the others, and so this is a very elementary thing in probability theory. I don't think I'm going to have to explain that to the distinguished audience here today. So, but we get these numbers, the a1 through an, and they are non-negative number. And each one, does somebody want to say something? Okay. So now the theorem. Okay. Now the mean. The average number of heads is obvious, and too, and that's the sum of all the probabilities, because we got chance p1 that we're going to get a head on the first and p2 on the second, and we add these all up, and this is the average. So this is the mean, or the average expected number, whatever you want to call it. And so here's my theorem. It says that if k is less than or equal to mu, then ak minus 1 is strictly less than ak. So, for example, suppose that I've got 100 coins here, and maybe maybe this mu is like 31.6. So I'm saying that if you're less than the average or equal to the average, then so your chance of getting 27 coins is bigger than the chance of getting 26. The chance of getting 28 is bigger than 27. 30 is bigger than 31. Now, also, if k is greater than or equal to mu, then ak plus 1 is less than ak. It says that after you pass the average, it's going to go down. Your chances are going down. Now that's the second statement is actually equivalent to the first, because if you change heads to tails, you are just changing all the q's to p's. And excuse me, Sean, I keep hearing myself sort of with a buzz. Is that a problem? It's okay now. Yeah. Okay. So changing heads to tails just reverses all the coefficients. An becomes a0, an minus 1 becomes a1, and so on. So anything that goes and mu changes to n minus mu. So anything that happens at the beginning of the sequence is going to, the same thing is going to occur on the other side. But anyway, this is a result that's sort of intuitively obvious, but I had never heard it. I knew it in special cases, but I never had heard it before. And this has many corollaries that I'm going to get to later. So before I go to the corollaries and applications, let's try to prove this result, because the proof is also very nice. Is it clear what I'm trying to prove, though, first of all? That if you're flipping coins and you want to know what's the odds of getting k heads, and k is less than or equal to the average, then that's bigger than your chance of getting less than k minus 1 heads. Strictly bigger. let's see. This is weird. Let me see. Is this? Let me just check that it's correct. when all the p's are 1 and when q's are 0. Because I'm a little worried there. If all the p's are 1, that means I'm always going to get n heads, right? So an is 1. And then all these others, a's are 0 here. And so I had better... what? Yeah, but it's strictly... okay. Or ak equals 0. Or they're both 0. Or both are 0. So there is this little exception. That's one of the great advantages you have of when you give a lecture. You always think of something that you don't think of when you're writing the book. Okay. So, but it's going to be strict. It's going to be strictly less than in the interesting cases, and I'm going to want to know that. So trivially, we can have some zeros at the beginning or at the end. I mean, all the p's could be 0 as well. So we got the same caveat, both 0. Okay. Now, but let's consider first the case when all the probabilities are equal. So first, case 1 is p sub j equals p for all j. All right. Well, that's easy. What's this polynomial in that case? So that's q plus pz raised to the nth power. And we know the binomial theorem, so that is the summation of, n choose k, p to the k, z to the k, q to the n minus k, which is, so a sub k is the coefficient of z to the k, which is n choose k, p to the k, q to the n minus k. I'll write that as n factorial over k factorial, n minus k factorial, p to the k, q to the n minus k. Now, so let's check it. Let's check if our result works. What is mu? Mu is equal to n times p, the average. And ak minus 1 divided by ak, we just plug in. So I got n factorial, k minus 1 factorial, n minus k plus 1 factorial, p to the k minus 1, q to the n minus k plus 1, and then I got to divide by ak, which is n factorial, k factorial, n minus k factorial, p to the k, q to the n minus k. Lots of cancellation occurring here. So the p to the k goes out with this p to the k, the q to the n minus k goes out with this q to the n minus k. The n factorials go away. The k factorial almost cancels with k minus 1 factorial, and the n minus k plus 1 factorial almost cancels with this guy. So so I'm left with q over p, k over n plus 1 minus k. Now I want to show that if k is less than or equal to mu, that this is less than 1, strictly less than 1. So the thing is, if k is less than or equal mu, then k over mu is less than or equal to n plus 1 minus k over n plus 1 minus mu. This is true if I put any number in place there, because you multiply it out. What do you get? K times n plus 1 minus k mu. Multiply this by this, and that is supposed to be less than or equal to mu times n plus 1 minus k mu, and that certainly is true, n plus 1 being positive. So here's something that I can use. Also, what about q over p? Well, q is n minus np. I'm sorry. Yeah, q is Q over P is 1 minus P over P, which is n minus mu over n minus mu over mu, because you multiply both the numerator and denominator by n and you get this. So then in my proof then I have a k minus 1 over ak is equal to q over p times k over n minus 1 minus k, and this is equal to n minus mu over mu, and k over n minus 1 minus k. Well, let me just make that less than or equal, because k over n minus 1 minus k is less than or equal to mu over n plus 1 minus mu, right? So this is equal to n minus mu over n plus 1 minus mu, and it is definitely less than 1. That was what we wanted to prove, strictly less than 1. So ak minus 1 is less than a sub k, unless they're both 0, which could happen if p is equal to 1, as we observed before. Now, so we proved this result in the case where all the probabilities are the same, and now we want to prove it the other case where the probabilities are not the same. So now let's suppose that that I've got two probabilities, P1 and P2, that are different and also different from 0 or 1. 0 and 1 are trivial cases that there's no chance when the probability is 0 or 1. So suppose we have this condition, then we consider another set of probabilities. So I'll take P1 prime to be P1 minus epsilon, and P2 prime to be P2 plus epsilon. And then, of course, Q1 prime is going to be Q1 plus epsilon, and Q2 prime is Q2 minus epsilon. But I subtracted, epsilon is some terribly small number. I subtracted epsilon in one case and added it in the other case because I still have the same mu. Mu prime is P1 prime plus Pn prime is the same as P1 through Pn. So I haven't changed the average. I'm just changing that, making this first coin a little less, tiny bit less probable, the second coin tiny bit more probable. So let's compare, what the different coefficients are, and let's figure out what's ak prime. AK prime is equal to AK. Now here we have, we can work it out. It's tedious to go through the details, but I'll show you how it starts. So come back to this in a minute. Let's start out and figure out what we've done. So Q1 prime plus P1 prime Z times Q2 prime plus P2 prime Z is equal to Q1 plus epsilon plus P1 prime. Let's simplify it a little bit. Q1 plus P1 Z plus epsilon times 1 minus Z. And then the second term is same deal, Q2 plus P2Z, but now minus epsilon times 1 minus Z. And so this turns out to be equal to what we had before, Q1 plus P1Z, Q2 plus P2Z. And then I actually want to work out the other term exactly, but I won't bore you with it. You have to trust me. It turns out to be epsilon times P1 minus P2 minus epsilon times 1 minus Z squared. And you can check that out with any of your favorite computer algebra system. But it's nice because it factors in this way. And therefore, I claim that AK prime is equal to AK plus epsilon times P1 minus P2 minus epsilon times some factor alpha k, where alpha k comes from, I mean, here you see, you multiply this by all the other guys, Q3 plus P3Z and all the others, and so the same thing occurs here, P3Z and all the other, and on the last term too, and so what's the perturbation in these coefficients? It's something that's epsilon times P1 minus P2 minus epsilon times something that has nothing to do with P1 and P2. So this is alpha k is some function of P3 to Pn, but P1 and P2 don't appear there. So now the point is, I'm going to try to find well, the difference between alpha k prime and alpha k minus 1 prime. I'm going to try to make this extreme. I'm going to try to make this, let's say, as small as possible. Because if I make it as small as possible and it still is positive, then that's what I want to prove. If my result is wrong, this is going to have to go negative. So anyway, I'm going to look I'm going to consider all choices of all my probabilities in such a way that this number comes out to be as small as it is, and I'm going to show that that's still positive. And so what is it? It's equal to ak minus 1 plus epsilon times P1 minus P2 minus epsilon times some, beta k, the difference of alpha k and alpha k minus 1. So now, if beta k is not 0, then I can't possibly have found the worst case of these probabilities, because because if beta k is not 0, I can choose epsilon to be some small number, and this is going to be smaller than this guy. I mean, it depends if beta k is positive. P1 is less than P2, so this guy is definitely negative. So I choose, if bk is positive, then I could choose, epsilon to be positive, some positive small number. If bk is negative, I can choose epsilon to be some negative number. But certainly, if bk is not equal to 0, I'm not at, I'm not at an extreme point. But on the other hand, if beta k is 0, then I can choose epsilon so that either P1 prime equals 0 or P2 prime equals 1. Because you see how I chose, you see how so I can choose epsilon to be P1 unless that makes P2 get too big, in which case I choose epsilon so that P2 gets equal to 1. So in other words, so if bk is 0, if beta k is 0, then there's also an extreme point in which I have another 0 or another 1. So I keep doing this, and finally I get to the situation where I can't do it anymore, and that means that I have some probabilities are 0, some probabilities are 1, and all the rest are equal. You with me? There's got to be an extreme point in which all the probabilities are one of these three values, 0, 1, or p, some common value of p. Now, but that's the case I already proved it correct for. So this is the completion of the proof. Because if all the values are 0 or 1 or p, that means that I had a polynomial where well, the zeros and ones are really easy to, they're just little factors of that don't affect the final coefficient, and they affect mu in the obvious way. So any questions on this? I proved the amazing theorem that your chances of getting Moreheads always increase as you get closer and closer to the mean. Now you might say, okay, so what does that mean to me? And the next result will explain one of the reasons why I like it. And so for this, let me show you one of a page from volume 1 of the Art of Computer Programming. We'll see if we can zoom up on that. How close can you get in on that, Sean? Very good. Yeah, this is page 99, and I'm analyzing one of the first algorithm where I really thought it was simple and worth a non-trivial analysis, and that was the problem of finding the maximum of a set of n numbers. And it turns out that the algorithm we almost always use is we say, well, we compare the first number to the second number, and then half the time we might have to switch, but we always compare our current maximum to the third number, and maybe switch if necessary, and then compare that to the fourth number, and so on. And at the end, we want to know maybe how many times we had to switch during this algorithm. And it's like flipping a coin, because when you compare the first number to the second number, half the time you're going to have to switch. After you compare the max of those two to the third number, 1/3 of the time you're going to have to switch. And so you get a histogram like this, where saying, certain odds that you never have to switch. The first guy was already the biggest. This is the case where there were 12. You're trying to find a maximum of 12 guys. Secondly, though, maybe you had to switch once or twice or something like that. But it looks like, it peaks here at 2. So, in fact, now we know that any histogram for a sequence of coin flips is going to go up, and then it's going to come down. And furthermore, we know that the place is going to where it's going to change from up to down is there at mu. In fact, you see what we've shown is that the maximum of A1 or A0 through AN is either equal to A sub floor of mu or A sub ceiling of mu. If mu is an integer, we know that the maximum occurs right at that integer point. But if mu is 3.1, then the maximum is either going to be A3 or A4. Now, I also worked out a formula here for what those probabilities are, and in that particular case of the finding the maximum problem, well, as I say, it's a coin flip, and you can write the thing as like this: z plus 1, z plus 2, up to z plus n, and then I'm sorry, let's go z plus 1 up to z plus n minus 1 divided by n factorial. And the coefficient of z to the k will be the probability that we needed to switch our maximum k times. It's the same as writing z times z over 2 plus, 1/2 plus z over 2, and then 2/3 plus z over 3 up to n minus 1 over n plus z over n. So when we make the last comparison, we have a chance 1 over n of having to switch. So now, so this was the generating function for how many times I'm going to have to switch when finding the maximum, and the coefficients here are well known as the Stirling numbers. The coefficient ak in that case is the Stirling number n over k with brackets around it divided by n factorial, and these numbers n over k with brackets are are well known to be also the number of permutations on n elements that have exactly k cycles. So these numbers occur all over the place in mathematics. So now, so we have and what's mu? Mu is equal to 1 plus 1/2 plus up to 1 over n, the nth harmonic number. So it says that if k is less than the nth harmonic number, which is very close to the natural log of n plus Euler's constant, so if k is less than that, then the Stirling numbers are getting bigger. And if k is bigger than that, the Stirling numbers are getting smaller. All right. Now, in fact, when I wrote volume 1, I could only calculate up to n equals 11. I think I might be off by 1 here, ak plus 1 or something. But anyway, I took the case of n equals 12, but now it's real easy for me to go to my computer and calculate all these Stirling numbers for n equals 100. So so let me show you the same thing for n equals 100. So these are the Stirling numbers, the Stirling cycle numbers when you have 100 elements. So how many permutations on 100 elements have 1 cycle, 2 cycles, etc. The natural log of 100 is twice the natural log of 10, so it's about 4.6 or something like that. And you add Euler's constant, and you see why there's a big peak there. But we can go a lot further because we could also say, well, what about if we bias these things in a strange way? For example, we replace z. So we have any function f of z is a0 plus a1 z an z to the n. Now let's replace z by c times z for some constant c. So a0 plus a1 c to the an c to the n z to the n. Now if we now normalize by dividing by f of c, so we have f of c z over f of c, we get b1, b0 up to b and z to the n, where now these represent probabilities again, because I could refactor. So where I had before, I had qj plus pj z for a certain coin, but now I've got a c in here, so I divide by qj plus pjc, and again this corresponds to some other probabilities, qj prime plus pj prime z. The only point is that the sum of these two coefficients has to be equal to 1. And so if I divide by f of c, I can convert many different problems into the same problem about coin tossing. So if you have any polynomial whatsoever that factors into linear terms, and the linear terms have non-negative coefficients, no minus signs in here, then that same result is going to hold true. So the coefficients are going to get bigger, and then they're going to get smaller, and the place where the peak occurs is going to be at what we call mu. Now, what is this mu? It's equal to. We can find it by calculating the average of this, which means that we differentiate with respect to z. So f prime. You take the derivative with respect to z, we get c times f prime of cz over f of c is equal to b0 plus, it's equal to b1 plus 2b2 z plus n bn z to the n minus 1, that's the derivative. And then if we set z equal to 1, we get the average. And so mu, in this case, mu sub c is equal to c times f prime c over f of c. So f was this given polynomial, and if we now say, well, what if I'm not interested in Stirling numbers n k, but instead I'll multiply by 2 to the k? Then I'm skewing the distribution, making the right-hand Stirling numbers, more and more important, giving them the next one twice as much significance, 4 times, and so on. And so the mean is moving to the right. And how far is it moving to the right? Well, instead of working it out, let me just tell you what it is. The mu, in the case of Stirling numbers, turns out to be equal to simply you start out with 1 over c and 1 over c plus 1, and you go up to 1 over n plus c minus 1. So if set c equals 2, then it says that you didn't really shift the thing much to the right. You only shifted it by adding n plus 1 and subtracting 1 at the end, so it didn't change by much. But here's an interesting thing. What if I shift by n? What if I consider the set of numbers n, the Stirling number n bracket k times n to the k? Now, so like n is 100, and I'm saying that I'm starting out with 100 Stirling 1, and then I'm taking 100 Stirling 2 times 100, and then the next one is 10,000, and so on. So what does it look like there? And here's another histogram that corresponds to that case. So if you skew it, you're finding out that it's always growing up until it comes to a maximum, and then it comes down after the peak. Where's the peak? If we look here, it's going to be at 1 over n plus 1 over n plus 1 plus 1 over n over 2n minus 1, if we skew it by n. And well, this is something that we can work on, because this we can say this is equal to 1 over, let's try it when n equals 5. It's going to be good enough for me to show you what's happening. So 1/5 plus 1/6 plus 1/7, 1/8, 1/9. I'm going to write that as 1 plus a half plus 1/3. I should have taken 4 instead. And then I'm going to subtract 1, but I'm going to subtract off 1. I'm going to subtract off 1/2, which is 2/4. I'm going to subtract off 1/3, which is 2/6. I'm going to subtract off 1/4 as 2/8. And so I think you can see how I got from this line to this line. And so this is equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and minus plus minus plus to plus 1/9. This is, as everyone knows, approximately the log of 2. I mean, this is a famous result going back to the 17th century of the formula for the log of 2, approaching pretty rapidly, bracketing the value of log of 2. And therefore, the mean, I forgot, by the way, that I have to multiply it by, I really meant multiply this by n. Didn't I? No, I didn't. No, I'm sorry. I've got to multiply it here. Mu c is c times this. I forgot the factor of c in that formula. And so here's my formula. I have an n on there. So what I've got is, what I've now shown is that when you take the Stirling numbers and you weight them by n to the k, then the mean shifts way over until the point where it comes out to be log of 2, which is 0.693 times n, is where it occurred. Now, but it gets there's much more to come. So next thing, let's take f of z to be any is some polynomial a0 a1 z up to a n z to the n, where let's say that all coefficients are greater than or equal 0, and I'll say that a n is greater than 0. And I'll say that f has n real roots. So all of it, this polynomial has no complex roots. All of its roots are real. Then the theorem applies that a0 less than to a mu and a ceiling of mu greater than up to a sub n, and here I don't know, and mu is equal to f prime of 1 divided by f of 1. And so what I have to show is just that if f has n real roots, I can reduce it to the coin tossing problem that we had a minute ago. Well, I just have to observe that none of these roots can be positive. The only roots it can have are 0 or negative. You see, let's suppose that a n is equal to 1. I can normalize, suppose a n equals 1, then we'd have f of z is equal to z minus r1, z minus r2. We just factor it into its roots. And I want to say that none of these roots can be positive. Well, you see, f of a n is 1. If z is, I guess I could use the x instead of z, but we start out at 0, and the value f of 0 is 1. And as x gets bigger than 0, f of x gets bigger than 1. So it's never going to equal 0. So it couldn't possibly have a positive root. So all of these guys are 0 or negative. All these r's are negative, and so in other words, we can always write this as if it were z q. Okay, so f of z over f of 1 is equal to z minus r1 over z over 1 minus r1, and so on, z minus rn over 1 minus rn. Remember, the r's are negative, and so this is just q1 plus p1z for some choices of these q's and p's. So the same, dividing by f of 1 converts it into the coin tossing problem that we had before. So here's a nice result. We don't have to know anything about the coins that we're tossing. We just have to know that we have some polynomial given to us that has all real roots, and all of a sudden we can solve problems about polynomials because we started out thinking about probability theory. But so now, in other words, you don't have to have a probability problem in order to find probability theory of use to you. And the other, in fact, there's other kind of Stirling numbers. The Stirling numbers with the curly brackets instead of straight brackets, and this represents the number of ways to partition a set of n elements into m subsets. Now, these numbers, the Stirling numbers, have the world's record as being having the most people discover them because they arose in a different problem, and through the ages, they, in fact, earlier this year, I got a letter from a Harvard physicist saying he's run into an interesting sequence. Have I ever seen it before? And sure enough, he had discovered these Stirling numbers. in yet a different way. And he was looking at some Feynman diagrams and some interaction. And so I also told him that now on the web you can just take any triangle sequence that you want, like So here's the book Concrete Math has Stirling triangle for subsets here, for example, and you can take this and you can key in. You can leave out the zeros if you want. So you type in 1, 1, 1, 1, 3, 1, 1, 7, 6, 1 to the Encyclopedia of Integer Sequences online lookup feature, and it'll say these are the Stirling numbers, and it also represents the subsets. How many ways to partition a set into subsets, and it also will give you other interpretations, and it'll give you references to the literature, and so now we can compute our way into the mathematical literature using the internet, for cycles you also have the same kind of thing. Now, what about these numbers? Well, if I could show that these polynomials also have only real roots, so here my polynomials are different. I can't factor them in any obvious way. So here I have like x cubed plus 3x squared plus x for n equals 3, f3 of x, and f4 of x is the next case, which is x to the fourth plus 6x cubed plus 7x squared plus x, and so on. I would like to show that these polynomials have only all real roots. They certainly have non-negative coefficients, and leading coefficient is 1. In this case, the Stirling numbers satisfy a easy recurrence based on the interpretation about partitions, and fn plus 1 of x turns out to equal x times fn of x plus fn prime of x. Now I'm going to show you that this recurrence, it means that all the roots of these polynomials are real, and that the proof is real slick. It goes like this. Suppose g n of x is equal to e to the x times fn of x. Now, I'm going to assume, by induction, that fn of x has n real roots. So if we plot gn of x, it will also have n real roots. So fn of x is going to be like this. And what's the deal? And so fn of x has n roots, and they're all so fn of x, it's a polynomial, and when x goes to infinity, it's positive. But then it has roots, so it goes negative at the first root, it goes positive, so like f4 had 4 roots, so it looks like this. And f5 is going to have 5 roots, and it's going to come this way. But now g is going to, so this is sort of the f4 of x is something like this. And g4 of x, what's it going to look like? Well, we're multiplying by a factor e to the x. So g of x is going to go way big at the, it's going to also come like this. And then it's going to come back down, though, as x goes to minus infinity. It's going to get very close, but not equal to 0. So look at g prime of x. Gn prime of x is equal to, okay, what happens? We e to the x times fn of x, and the next term is e to the x fn prime of x. So gn prime of x is going to be this, and you see g4 prime of x is going to be the place where this curve is flat. And so here's one place here, here's 2, 3, here's 4, So it's got 4 real roots as well. Oh, wait a minute. Gn prime 1, 2, 3. I didn't. F4. 1, 2, 3, 4. Okay. Oh yeah. Okay. So this has 4 real roots, so in general it has n real roots, and I multiply by x, and I've got n plus 1 real roots, and so I've gone now from Fn having n real roots to Fn plus 1 having n plus 1 real roots. Okay, because the Gn prime had this, and I added this x here. It's another root equal to 0. So this proves then that these Stirling polynomials, my theory applies to the Stirling polynomials, and so I can figure out that the Stirling polynomials are going to have a peak that does this. And where is the picture? Right here. Here's a picture of the Stirling numbers for 100. So if you take a set of 100 elements and you want to know how many ways there are to partition it into m parts, it gets to its largest about between 28 and 29. And if you use my general formula for mu, which says calculate f prime of 1 over f of 1, it turns out that the mu in that case is equal to you can write it as this: the n plus first Bell number divided by the nth Bell number minus 1. The Bell number is one of these numbers that has no standard notation, but it's becoming more and more standard now to use this squiggly thing called variant pi to represent the Bell number, introduced by Louis Comte some years ago. And this is the sum of all of the ways to partition a set into any number of parts. So it's the sum of all the Stirling numbers. It's called the Bell number, and the mean now, it turns out to be equal to very close to the ratio of these two Bell numbers. And all of this comes out of this idea of flipping coins, that we were able to make this statement. Now, that's still not all. The first thing that people do when they see a table of numbers or a sequence of numbers typically is to form differences. So let's take, for example, the Stirling numbers for permutations on 5 elements. So you've got 24 permutations have 1 cycle, and 50 have 2 cycles, 35 have 3 cycles, 4 cycles, and here's the 5 cycles is the identity permutation. Now, let's imagine that we got zeros written before and after, and now we can form the differences of things. So 24 minus 0 is 24. 50 minus 24 is 26. 35 minus 50, negative 15. Minus 25, minus 9, minus 1. And we get zeros at the end here. I observed that no matter what row of Stirling's table you start with, it's going to look something like this. You're going to have a bunch of pluses and then a bunch of minuses. And the change from plus to minus occurs at the point, mu, at the point where, well, natural log of n in the case of Stirling number. But let's go on and take another difference. So 26 minus 24 is 2. Hope I get this right, minus 41. Minus 25 plus 15 is minus 10. Minus 9 plus 25 is 16, I hope. Plus 16, okay. And then 8, 1, 0, 0. Okay. So here we have a situation where I've got plus and then a minus and then plus. Do it again. And then you'll get the idea, so I'm not going to do it over and over, but I wanted to give it one more for whoops, no, this is plus 31 here. Minus 10 plus 41. Minus 16 plus 10 is plus 26 here. 8 minus 16 is minus 8. 1 minus is minus 7. And here I get minus 1. So here I got a plus and then minus, a plus and minus. So if you look at how many sign changes I've got here, I've got no sign changes in my original sequence. I got one sign change in the second. I got two sign changes in the third. Three sign changes in the fourth. Any guesses? It's going to be true that you take any polynomial of the kind we've been talking about. So any polynomial that has non-negative coefficients, it's not, the polynomial isn't zero, its leading coefficient is positive, and all of its roots are real. Then you look at the coefficients and you take differences, and if you've taken the differences k times, you're going to have exactly k sign changes in those differences. Now, just first to intuit what this might mean, in the case of second differences. The second difference is where the second difference says, is the increase bigger or less than, is the increase from ak to ak minus 1 to ak bigger or less than the previous increase? And so that you're comparing a difference to a difference. And so you see what's happening here is that as we begin this sequence, it is a concave sequence, which means the second difference is positive, which means that we keep on growing faster and faster as we're getting towards the mean. However, after a while, it starts to taper off, and then in the middle, it's a convex sequence. The second difference gets negative, and then again, it's concave at the end. And this is informally, it's a bell-shaped curve. And so the result that I'm going to prove next is that the second difference always has this property. It starts out plus, then it's minus for a while, and then it's plus again. There's always two changes of sign, and it also works. Third difference will also be. So every time you have something that has this polynomial, with all real roots and all the coefficients are non-negative, the coefficients are actually going to be a bell-shaped and even more generalized if you look at third differences, fourth differences, and so on. Now, so let's let C of f is this polynomial. So f is equal to a0 plus a1x, an x to the n. C of f is going to be the number of sign changes. And it in the sequence 0, 0 up to, and then a0, and go up to an, and then zeros again after that. So I consider this to be an infinite sequence with zeros afterwards, and sign changes. And I'm going to try to explain then. So if we look at the pattern here, we got zeros for a while, and then the first coefficient, let's say, is positive. And I'll write that as greater than, meaning greater than 0. And then if there's one sign change, there's going to be the first case where we have a negative coefficient. And so in between those two, these two might be next to each other, but otherwise we might have a few greater than or equals here, cases where positive or 0. So I might have a 5 and then maybe 0 and 3 and something, but then finally I get a negative number, and then I'm going to have some optional negative things, and then another positive one, and then some of these, and then a negative, and finally it's all zeros again after a while. So this is a typical case which has 1, 2, 3 sign changes. Okay. As for example. And so now I'm going to observe that if C of x, okay, I'm going to say that C of a plus bx times f is less than or equal CF. I'm saying that A and B are positive. so if I grow a polynomial by adding another linear factor, I want to see how this affects the number of sign changes. And I'm claiming that it never increases the number of sign changes. And, well, this is pretty easy. You can see that A and B are positive. So what we're getting, if we multiply this, we're going to take these coefficients and multiply them by, so we're going to have A times this coefficient plus B times the previous one. So that's going to be positive. The next one is going to be this non-negative plus this one is going to be positive too. If this guy exists, there'll be a positive here. But these will all be, so this first guy will, this is positive. This one here, we're going to have a problem at this point. I don't know what's going to be here. I'm going to multiply this guy by A and multiply and add B times this one. But this one was negative, this one is non-negative, so maybe, I don't know what the sign is, so there's a question mark right there. But these guys are definitely less than or equal, if they exist. Then there's a question mark here, and then there's some greater than or equals, and then there's a question mark at every transition point, I don't know. But then at the very end, we have a definite sign at the end that there's going to be one minus here somewhere. And so anyway, no matter what you put in for the question marks, you can't have more than 3 sign changes in this one. So I've proved this result. The other thing is C of 1 minus xf is always greater than C of f. That is, if you take a polynomial and then you multiply by 1 minus x, which is the same as taking the difference operation, that says you look at the coefficient and subtract the previous one, then you always increase the number of sign changes. So why is that? Well, we start with this plus and then some optional, and we have our first minus, and then some optional guys, and then another plus, and some optional, might not be there, and then minus. And now, after I multiply by 1 minus x, I certainly get positive here, and I certainly get negative here, because this is a negative, and I've subtracted a non-negative from it. And I'm going to get a positive here because it's plus in this here, and I'm subtracting a negative. And I'm going to have a positive here as well. And at the very end, I'm going to have a minus that's inherited from the fact that one of these guys was positive, and then after that I'm getting a minus. So I had 4 changes here. I'm sorry, 3 changes here, and I've got 4 changes here. So this is a proof that taking the difference always increases the number of sign changes at least by 1. Now, you start out with the constant function, and then you multiply by linear factors, and you say that. I'm sorry. No, I'm sorry. I start out with the function that's from my polynomial, and then I take differences 10 times. Then I have increased the number of sign changes by at least 10. But on the other hand, the number of sign changes of the polynomial 1 minus x to the mth is exactly m, and so that proves the result that I was claiming. Yeah. Greater than equal? No, it has to be strictly greater. So every time I take a difference, it's going to be 1 more. And let me show you the argument again. So I had a positive guy here, and then I had a negative guy here, and I had these guys don't necessarily have to be present, but they might be 0, they might be positive. But after I've taken the difference, I still have a positive guy here, I still have a negative guy here, I still have a positive guy. The first appearance is always there. But furthermore, one of these guys after I go out far enough, the first thing you hit from the right is negative. And so after I get, there's all zeros after a point. So your argument would be correct if this was an infinite sequence, and never approaching zero. But actually, we do get to a point where we actually hit zero, and so then zero minus this negative guy is going to be positive, and so that's where it kicks in. Yeah, I'm glad you asked the question, but that's the. So this argument proves then that we have exactly this number thing. Okay, now. Now that was my first of two examples of why I said hooray for probability theory this year. So just before I leave that one, let me point out again that what we were able to show then is that a great number of combinatorial sequences that can be expressed as the coefficients of polynomials, and you can show that those polynomials have only real roots. And usually they have only non-negative coefficients because you have some interpretation to those non-negative coefficients. It's the running time of a computer program or something like that. So whenever you can do that, and you can also prove that the polynomial has only real roots, then we know lots about those coefficients. We know that they're bell-shaped, and we know that we can locate the place where the maximum occurs and do some things like this with completely elementary methods. And there have been long papers trying to analyze where's the largest Stirling number of the second kind. This has and you can get into really complicated formulas, but now just by using this theorem, it happened. Now I should give credit to the sources of this. So the first theorem that I mentioned, which was about the, it gets bigger and bigger until you get to the mean, and then that goes back to a man named Vasily Hefting. Let me find the reference here. In, let's see, 55, yeah, 62. Okay, so this was 1956. That was when I was, entering college. My teacher should have told me about this theorem then. To apply, to go the next step, to show that it's bell-shaped, was taken by a man named John Darach, Australia, in 1964. These theories about sign changes in sequences actually go way back to Laguerre in 1883, and a 50-page paper he wrote in 1883, and then George Polya and Gabrasego had a section of their wonderful book, Problems and Theorems of Analysis, based on Laguerre's work. And then putting all these pieces together and showing how it applies to Stirling numbers, and how useful it is, and how it solves problems that combinatorialists have been beating their heads over in hard way for a long time, and many more. This was Jim Pittman in 1997. And then my friend Herb Wilf wrote me a letter in June which explained it to me. But these are, so these things go back, and so it's conceivable that that a lot of people in the audience already knew about these because the results are old, but they're elementary and useful in lots of ways. Okay. Now let me, yeah. Oh, by the way, there's a microphone in front of each seat, in front of each.
Hello. Yeah. Just about the attribution. I think such sequences are known to be log concave, and Newton also did some work on that to show that these sequences are log concave. So not only are they
log concave is the
slightly more, yeah. So I think it just goes slightly. Perhaps I'm wrong, but I think Wilf's book, Generating Functionology, has a chapter on exactly this topic. and they're actually, yeah.
Okay. Well, that's great. If you can give me, of course, I have the book generating functionality, but I didn't realize that that Herb had done that. Okay. So, all right, that's good to know. But I didn't know about is Newton's connection also mentioned in Herb's book?
Maybe not, but
okay. Yeah. Well, I hope you can stick around for a little longer and give me the information. Okay. Now, the other problem, I don't have much time to go into, but I have to tell you the highlights. You can find it on the web in the preview that I have of section 7251 of the Art of Computer Programming, which is where I'm studying the problem of generating all partitions. And in that section, I decided I wanted to give an exposition of the saddle point method for asymptotic formulas. There's one of the most powerful methods for finding asymptotic values of things is this thing from complex variable theory called the saddle point method. And most of the time, when you see a paper that uses it, that means that you have to slog through 20 pages of really hairy and ugly formulas and estimates in order to finally prove a nice result about the asymptotics. And and also the books that, there'll be surveys about asymptotics, and then they'll have, if it's a book, it'll have a chapter saying, introduction to the saddle point method, and saying, get ready for a hard subject. And I only know of one fairly elementary introduction to the saddle point method by a professor, what's his name, Wang in Hong Kong. But again, I never had seen a very good introduction to it. But I had found that many cases I needed the saddle point method, and I was hoping that I would someday be able to write an introduction to it that was the one that I wished that I had gotten. And so now it looked like here was my opportunity, because the asymptotic value of these Bell numbers that I was talking to you about, this variant pi sub n, is extremely interesting. It grows, slower than factorials, but faster than it's super exponential. It's a very interesting asymptotic growth, and saddle point method gives a very nice, a very beautiful way to understand exactly how fast these numbers grow. So this was my opportunity to write part of my book that gives an introduction to the saddle point method, and I had 2 or 3 pages where the formulas were all nice and clean, and also I could introduce in those same pages the saddle point method on a simpler problem as well, which was training wheels, where we already knew the asymptotic value, but we'd sort of say derive the asymptotic value of 2 to the n by using the saddle point method, and so on. Now, but then the next thing was to get the asymptotic value of these Stirling numbers. Not only to say where do these Stirling numbers peak, but how fast do they peak, and what if you're not at the peak? How big are the numbers? And for this, there were several papers, a dozen papers in the literature analyzing the asymptotics of the Stirling numbers, but they were all based on long, hairy analytic derivations that were not pleasant to put it, and it would take a long part of my book, and so normally I would just say, well, see such and such a paper, and this gives you the formulas. But even if you look at that paper, the formulas are horrible and ugly and hard to apply. So I thought, so I had a piece of luck, and I found a simplification as I was looking at the saddle point method, where I would be able to get formulas, asymptotic formulas for the Stirling number that were not only simpler than the ones I found in the literature, but also more powerful. The bounds on the error were sharper. But I still needed to prove a certain lemma in order to make this true. And I tried, and I worked for 2 weeks, night and day, and I couldn't find any counterexamples to the lemma. And it's, so I sort of knew that it had to be true, but finally after 2 weeks, I decided I had to give up on it. I had already put too much time into this, and so I couldn't afford. I had to get, life had to go on. I will now tell you what the lemma I needed, and then I'm going to show you how probability theory cracked the problem. Quickly then, I'm starting out with the saddle point method and the formula for n brace n. There's a closed formula that can be written this way: n factorial or m factorial times the coefficient of z to the n in e to the z minus 1 to the mth power. Now, this is a very well-known formula, and we get this by integrating. So to get this coefficient, now we have to go into complex variable theory, and that's 1 over 2 pi I times an integral of g of z to the n plus 1 dz, where g of z is the following formula. I believe it's log of e to the z minus 1 over alpha minus log of z. I think this is it. And where alpha is equal to n plus 1 over m. Yeah, because I got an alpha in the denominator. Okay, so now I want to integrate some function then around in the complex plane, and the key to this in the saddle point method is to find a place where the derivative is 0. So g prime, and we call this a saddle, and that's a complex number sigma, and so g prime of sigma is supposed to be 0. Well, g prime of z is equal to e to the z over alpha e to the z minus 1 over z, right? So that we can do, and then so now if I set this equal to 0, it turns out that the saddle point sigma is a root of now let's see. There's a whole bunch of beautiful formulas that instead of writing out, I will just show you from the book. If I can just find a page 40, 35, no, page 34. Page 34. It's page 30, no. Page 34 is sitting right here. So, I want to solve this equation: sigma over 1 minus e to the minus sigma equals alpha. And a huge number of problems in applications dealing with epidemics and random graphs and all kinds of other things are using formulas like this. And if you take the function x e to the minus x, you see it starts out at 0. And then when x equals 1, it's equal to 1 over e, and then it starts to decrease again, and it goes back and stays positive. And there are two values, alpha. I'll call this beta and alpha, that have the same value. Alpha e to the minus alpha equals beta e to the minus beta. Where alpha is bigger than 1, as it is in this problem, and beta is less than 1. And it turns out that if, in this case, sigma is also equal to alpha minus beta. So the saddle point that I need for studying Stirling numbers is given in terms of the two roots to this, to alpha e to the minus alpha equals beta e to the minus beta. And as I say, this arises in an amazing number of problems. And one such pair of values is take alpha equals log of 4 and beta equals log of 2. Then you can check log of 4 divided by e to the log of 4 is log of 4 over 4, and log of 2 over 2. These are equal. You see, so you have typical example of two numbers that satisfy this. And in fact, there's a general. If you take sigma to be the parameter instead of alpha and beta, you can write alpha equals sigma e to the sigma over e to the sigma minus 1, and beta equals sigma over e to the sigma minus 1. For any value of sigma from 0 to infinity gives you a solution alpha and beta and conversely. What I found was that I could, if I continued taking more derivatives, so I found g double prime of z, g triple prime of z. These are the values of these derivatives is what you need to figure out how the function is behaving around the saddle point when you plug in z equals sigma because of Taylor's theorem. So can you read this formula? G of sigma plus it, so at the saddle point plus a little up and down in the imaginary axis, we can expand it, and you see the higher order terms, the higher order powers of t are involving the kth derivatives of g at sigma. And the thing that I noticed was that g of sigma, well, okay, so you can calculate these derivatives and you can express them in many different ways, but there was one way was particularly simple, and let's see, it's in the answer page here. 79, 70, yeah, here we go. So gn plus 1 of z over n factorial is equal to minus 1 to the n times, well, let me put the sigma in there instead. Gn plus 1 of sigma over n factorial, which is what I need, is minus 1 to the n, and over sigma to the n plus 1, and then it's like 1 minus the summation on k of n bracket k alpha k beta to the n minus k. These are this is the other big triangle after the binomial coefficients and the Stirling numbers. The next important triangle is the Eulerian numbers, and the Eulerian numbers occur, and these are the number of permutations on n elements that have k what they call descents. It means that it goes down as you go from one place to another. So these, for example, the Eulerian numbers for n equals 3 are 1, 4, 1, and n equals 4, it's 1, 11, 11, 1. People keep discovering these numbers again a lot. This says if you look at the permutations in 3 elements, one of them has 2 descents. It's 3, 2, 1. It goes down twice. 4 of them have just one descent, and the case where there's no descents is 1, 2, 3. And similarly with 4 elements, you have a certain chance of having 1 descent, 2 descents, or 3 descents. Now, these numbers anyway occurred in this formula, and I had to prove that this quantity is small, divided by sigma. So, if I could prove that and alpha and beta are this strange function of sigma that I wrote down. You know, if alpha is this and beta is this, and as sigma goes from 0 to infinity, I was convinced that this particular combination of alpha and beta was monotonic, and it went from 1 to 0. So that then I would have a beautiful bound for this, because this quantity that I needed to bound was always between 0 and 1. Now, in these other book papers that I found in the literature, the authors had gone through long calculations with all kind of hairy analysis in order to prove not that this was between 0 and 1, but that this didn't grow too fast. You know, and so here, you know, I thought, you know, the Stirling numbers are one of the key things in mathematics. We've got to someday, you know, God wouldn't have wanted there to be no nice proof of their asymptotics, and there must be some, you know, some way that makes it come out clean. And all I needed then was to prove that this function is actually, you know, monotonic. Well, I wasn't able to prove monotonic, but I was able to prove that it's between 0 and 1. And it used probability theory, and that's my final punchline today. But I'll show you how it works. So there's a beautiful result that somebody named Tani discovered in 1973, and said that the probability that if you take random numbers between 0 and 1. So we call them uniformly random numbers between 0 and 1, u1 up to un. And so these are between, you know, real numbers, not integers, between 0 and 1. And you consider the probability that the floor of u1 plus un is equal to k. That this is actually exactly this Eulerian number, n choose k over n factorial. So you see what I mean? I'm taking random draws of n identical numbers, and then I add them all up, and what's the integer part of that number? And it's the same as the number of permutations, instead of the probability that a permutation has that many descents. And the proof is very easy, because you can imagine that I set V1 equal U1, V2 equals U1 plus U2 modulo 1. Throw away the integer part. V3 is same thing, mod 1. These numbers V1, V2, V3 are also uniformly distributed and independent of each other. And the number of times you descended is the number of times that V1 is the number of times, the number of times you had to actually drop down by taking mod 1 is the number of times the V's actually have descents. And so if you're looking at, if you look at all, at n space, at all the cases, and you identify the V's by the permutation, the volume of a set in n space in which any particular permutation occurs is equal to 1 over n factorial. So the chance that there are a certain number of descents is exactly the number of times that if V1 is greater than V2, then we've increased the floor by 1. So this is the proof. This is Tani's proof that gives you a connection between these Eulerian numbers and probability theory. Now, this means, okay, I want to evaluate alpha to the k, beta to the n minus k. What is that? It's the sum of these Eulerian numbers times alpha to the k, beta to the k. Our formula for alpha was sigma to the k, e to the k sigma over e to the sigma minus 1 to the k. And beta to the n minus k is sigma to the n minus k over e to the sigma minus 1 to the n minus k. So this is equal to, so a lot of things cancel here, and this turns out to be summation n to n Eulerian k, e to the k times the saddle point times this constant factor sigma to the n over e sigma minus 1 to the n. This thing here to the n. So I need to bound this quantity, but you see what I can do is this. If I have any function and I consider f of x1 plus, f of I want to know the integral of f of the floor of x1 plus xn dx1 dxn, and I integrate over the n-dimensional cube, 0 to 1. This is equal to the sum. This is equal to f of 0 times the probability that the floor is equal to 0 plus f of 1 plus times the probability that the floor of these guys is equal to 1, and so on. Because of, integrating these real values over this quantity. So it's equal to, in other words, it's the sum of f of n times n, f of k times nk over n factorial. That's the formula that I needed in my proof. So all I had to do was write this strange quantity as an integral. And I can write this as the integral from 0 to 1 of dx1 through dxn of e to the floor of x1 plus xn times sigma. This way. By the formula I just gave. So this integral equals that sum, and well, this happens to be less than or equal to the same integral without the floor. And this is just the integral of e to the x sigma from 0 to 1 taken n time, which is e to the sigma over, or something like this. I can't remember, but just exactly the factor that I needed to give the upper bound. And similarly, the lower bound, it's greater than or equal to the same thing, but I subtract 1. And again, you gave exactly the lower bound I needed for the asymptotic. So here was a case then that I'm working an algebraic problem. I come up with these Eulerian numbers. Then lo and behold, I once learned that there's a way to relate Eulerian numbers to the probability that permutations have a certain number of descents. Therefore, I can write as an integral. Sorry, it's also the probability that uniform random numbers have a certain floor, and therefore I can write it as an integral, and that leads to the bound. So the end of the story then is just that now there's a formula for Stirling numbers, which is completely uniform. I've got the formula on page 35, so all I have to do is display it for you, and then we can quit. There's got to be a page 35 in my site here. 35. So the final formula for Stirling numbers then is this formula here. Whoops. you got to turn your. Yeah, I'm sorry to make it hard on you. This is the leading term is actually easy to evaluate once you understand alpha and beta, and then these other terms. The main point is that now the b's are known to be well behaved, and this works over the entire range of from m equals 1 to m equals n, and it says here in that formula 43 looks a bit scary because it's designed to apply over the whole entire range, but significant simplifications are possible when m is small or large, and those are also not hard to work out. But I had to end with something a little scary because it's Halloween tomorrow. Okay, sorry that I didn't make it as easy as I thought it was going to be, but I think at least you can see why I was in love with probability theory twice this year. Thanks.